Mechanism of nucleophilic substitution reactions of alkyl halides. Mechanism of nucleophilic substitution reactions of methyl halides is always SN2 because methyl halides are most reactive towards SN2 reactions. Mechanism of nucleophilic substitution reactions of tertiary alkyl halides is always SN1. Tertiary alkyl halides are most reactive towards SN1 reactions. When we compare the rate of SN2 reactions of methyl halide, primary alkyl halide, secondary alkyl halide and tertiary alkyl halide having a common halogen atom, it decreases from left to right. That is, methyl halide is most reactive, followed by primary, then secondary, then tertiary. However, rate of SN1 reactions increases from left to right. Methyl halide is least reactive towards SN1 reaction and tertiary alkyl halide is most reactive towards SN1 reaction. Hence, mechanism of SN reactions of methyl halide is always SN2 and that of tertiary alkyl halide is always SN1. The mechanism of SN reactions of primary and secondary alkyl halide may be either SN2 or SN1. Depending upon the nature of nucleophile and nature of solvent used, mechanism of SN reactions of primary and secondary alkyl halides can be either SN2 or SN1. It can be determined experimentally. In a typical experiment, rate of reaction is measured by changing the concentration of nucleophile without changing the concentration of alkyl halide. A series of experiments are conducted by changing concentration of nucleophile without changing the concentration of Rx. In each case, rate of reaction is determined. Rate is change in concentration of reactant or product in unit time. Suppose in first experiment, concentration of alkyl halide is A mole per liter. Concentration of nucleophile like OH minus is B mole per liter. Suppose the rate is found to be R1. In the second experiment, concentration of alkyl halide is same, that is A mole per liter, but that of nucleophile is changed from B to 2B, that is concentration of nucleophile is doubled in the second experiment. The rate is found to be R2. In the third experiment, concentration of alkyl halide is again A mole per liter, but that of nucleophile is tripled, that is 3B mole per liter. Suppose the rate obtained is R3. Similarly, a series of experiments are conducted. Suppose the results obtained are like this. R2 is equal to 2R1, R3 is equal to 3R1, etc. Then it follows that rate of reaction is proportional to concentration of nucleophile. That is, mechanism of the reaction is SN2. Suppose the results obtained are like this. R2 is almost equal to R1, R3 is almost equal to R1, etc. In this case, it follows that rate is independent of the concentration of nucleophile. That is, changes in the concentration of nucleophile does not affect the rate. Both R2 and R3 are equal to R1. Hence, the mechanism is SN1. That is, Mechanism of SN reactions of methyl halide is always SN2. That of tertiary alkyl halide is always SN1. The mechanism of primary and secondary alkyl halide can be either SN2 or SN1. It is determined experimentally. Rate of reaction is measured by changing concentration of a nucleophile without changing the concentration of alkyl halide. The result obtained is then compared. If rate of reaction changes with changes in the concentration of nucleophile, then mechanism is SN2. If rate of reaction does not changes with changes in concentration of nucleophile, the mechanism is SN1. Mechanism of nucleophilic substitution reactions of allylic and benzylic halides is always SN1. It is due to greater stability of allylic and benzylic carbocations. Both allylic and benzylic carbocations are stable due to resonance. This is allyl chloride. It readily undergoes dissociation to form allyl carbocation. This allyl carbocation is stable due to resonance. The positive charge can be delocalized through resonance. Hence, allylic halides CH2 double bond CH CCl. The two valencies may be satisfied by hydrogen or alkyl group. This type of compounds are called allylic halides. They always follows SN1 mechanism in their nucleophilic substitution reactions. It is due to the greater stability of corresponding allylic carbocation. This compound is benzyl chloride. Benzyl chloride also undergoes nucleophilic substitution reactions through SN1 mechanism. Heterolysis of carbon halogen bond in benzylic halides results in the formation of benzylic carbocation. In this case, benzyl carbocation is formed. Benzyl carbocation is stable due to resonance. Due to resonance, the positive charge can be delocalized to ring carbon atoms. This type of resonance accounts for greater stability of benzylic carbocations. So due to extra stability of carbocation intermediate, benzylic and allylic halides undergoes nucleophilic substitution reactions through SN1 mechanism. In the case of benzylic halides, the corresponding benzylic carbocation. This type of compounds are called benzylic halides. Benzylic halides can form stable carbocation intermediate and hence they prefer SN1 mechanism in their nucleophilic substitution reactions.